Hello, and welcome to a new lesson of hands-on optimization. I'm Cristina Radu, and we have here Felipe Brando from AMPL. So let's get started. What are we going to talk about today? We will continue adding constraints to our model. So we will add the production hours, model the capacity, and we will show you a few tricks that you can use using Slack variables. So how to turn a hard constraint into a soft one, but also how to debug using those Slack variables. And at the end, Felipe is going to show you a few tricks about shelf life, which is a little bit complex to model. So this way we already added it so early in the class, because if we add other things and then the shelf life, it becomes super complex. So we just wanted to keep it simple so you understand the concepts and then, yeah, apply them whenever you need. Okay, so the first thing we can do is to check the homework. So you had to write three constraints: the demand constraints, the inventory carryover. So when the starting inventory of the next bucket is the ending inventory of the previous bucket, and the material balance, which is the equation that is the core of the solver and brings all the concepts together. So for the demand, um, I think we already said it, but let me read it again. So the demand, which is an input, and it's by product, location, and period, equals the met demand and the unmet demand. So all the variables have the same dimensionality, and it's the same for the constraints, right? Because sometimes it can happen that the variables and the constraints, they have different dimensionality, and then you need to sum up. I'm actually going to explain in a bit how this works. And inventory carryover, here you have like a logical condition. So basically, if the period is 1, then in that period, the starting inventory is the initial inventory. This is what comes from the ERP system or from whatever system. So this is what you start with at the beginning of your planning horizon. And then in the other periods, ending inventory equals, sorry, the starting inventory of one period is the ending inventory of the previous period. Maybe here it's not visible. Okay. And the material balance, as we said, always the planner wants to check the ending inventory. And how do we express that? It's the starting inventory where you add production and you subtract met demand, not demand, because it can happen you have unmet demand, and then you actually put a penalty in the objective function for the unmet demand. So the solver is trying to minimize the unmet demand. Sometimes it meets it, sometimes not. So then in the equation, we talk about the met demand. Okay, let's move to the next slide. Production hours and available capacity. So here, let me move this again. We need to model production hours and production. So the variable production is in quantity, in units. And then we also have production hours. And the way those two concepts are related is by rate. So rate is units per hour. And as I said, you need to sum. So production hours is on product, resource, location, and period. And then here in the first constraint, we sum by resource. So basically we are talking about the production in all the resources in that certain location. So that's the production quantity. And then if we want to cap the capacity, we have here an input, available capacity. And here I want to make a comment. This available capacity is actually the total capacity. Let's say you have 168 hours per week, and then you need to subtract maintenance, cleaning, maybe changeovers, and so on. So there is a little bit of calculation, and you usually have this total capacity, which is like the maximum capacity, and then you need to read data from a calendar and subtract what is not available, and then you end up with this available capacity. And then here you also need to sum by product, right? Because production hours, the available capacity is per resource. So you know that per each resource, I can use this week 120 hours. So then the production hours need to be summed. So for all the products that are on this resource, I have this much available capacity. And we also have in the app a report which shows you an overview of the resource utilization, because this is usually the first thing that planners check. I told you that they check the ending inventory, and if there is everything looks fine, okay. But even if the ending inventory is fine, they still check the resource utilization, because here you want to have a balanced plan, right? You don't want in one week to have 100% utilization and the next week 13% utilization, because if you have that, it can also mean there is a problem, because sometimes the not sometimes, or yeah, let's say in many cases, for each resource you also have a labor resource, right? So then you need to plan it many months in advance, and the labor pattern needs to be quite constant. So you cannot say this week I use 2 people and next week I use 20 people, right? So many companies want to have this balanced resource utilization, because it comes with the labor utilization, which they need to plan many months in advance. You cannot just call somebody today to come tomorrow. So this is just a comment about this. Oops. Okay, now the topic of Slack variables. As I said, we can use them to turn constraints from hard into soft. And the first example is the demand. Because normally you want your met demand to be equal to the demand. So if we write it like that, this is a very hard constraint. Because if the solver cannot meet the demand, for example, because you have capacity limitations, then the solver goes infeasible. So what you do is that you add a slack variable, and you say that the demand equals met demand plus the unmet demand. And then we have now a hard constraint becomes a soft constraint. And what you do is you add a penalty for the unmet demand in the objective function. And in solvers which are based on unit optimization, this is the highest penalty you put on unmet demand, because you, of course, you want to minimize it. So for example, here we have, I put 10 for unmet demand plus 5 plus ending inventory. But depending on what you have, of course, when you have more terms, you need to come up with other numbers, and you can put like 1,000 for unmet demand and 5 for ending inventory. And the objective in this case, it's by product location, which is the same dimensionality as the variables unmet demand and ending inventory. As we will see, this doesn't happen all the time. So let's take another example, what we just discussed, capacity, where we do have a hard constraint. We have production hours is less than or equal than available capacity. And this is hard because you cannot go above. But sometimes, for example, when you do an RCCP, rough cut capacity planning, which is planning a long time into the future, you don't need to be that exact. If you go, let's say, 5% over your capacity, it's fine because you can reorganize things. So then you can add a slack variable, how we did with the demand. And we have then production hours equals available capacity plus above capacity. And then we transform the hard constraint into a soft one. And we need to add a penalty in the objective function. So here, if I start writing the objective function, I see a penalty for unmet demand, I have an inventory, and above capacity. And then I see that maybe the dimensionality doesn't fit very well, so I need to check, right? Because the unmet demand is on product location, ending inventory product location, and this one is by resource. So we need to align. And in this situation, then we need to start summing up the terms in the objective function. So I sum the unmet demand by product. So this means that I get here the dimensionality location, then the ending inventory, the same by location, and then the above capacity, which are also by resource location. I sum by resource and I end up for location, meaning that for each location, I need to minimize this expression. We didn't put this in the homework because again, it becomes a little bit complex, but just for you to understand how to use the slack variables and also this alignment of dimensions, which in this case happens in the objective function, but it can happen also in the constraints, that the constraint has a different dimensionality than the variables, and then you need to sum the variables such that the dimensionalities match. Okay. And we can use the slack variables when debugging, because sometimes you add a super complex constraint, and then you don't know where is the problem. Because when you have a big constraint like how I'm showing here, there is a lot of data coming in, and sometimes it's fixed data, right? Like input data, and then data is not always clean or consistent, and the solver can go infeasible. So what can you do? And here I used the material balance and I wrote it in a way that it's almost as it looks in a real life implementation. And I will just talk about, for example, production. In each bucket, you have confirmed production, which can come from the ERP system. So this is fixed, this is an input. And then you have the planned production, the decision of your solver. And for each concept, you have the same. What comes from the ERP system, it's confirmed, it's promised, it's done, and what the solver can plan. And then if you add all this kind of confirmed production, confirmed purchases, shipments, transfers, and so on, as I said, there is data which maybe is not correct. And then the solver is infeasible. So what you do, you add this virtual supply, I call it. You can call it whatever. And then you run it and you see suddenly this virtual supply is different from zero. If it's zero, it means the problem is not in this constraint. But if it's different than zero, you need to start digging. Where does it come from? And you start eliminating terms from here to see from where does this virtual supply come from. Okay, and now the topic of shelf life. This is a very important topic in a lot of companies, and in particular, fruits and vegetables, meat and dairy, they have a very sensitive shelf life. So you need to model it, but this is not a trivial way to. It's not a trivial concept to model. And as I said, we put it now at the beginning of the solver because otherwise, if we add the other concepts and then this one, it becomes very hard to follow. And as Felipe will show you, he created the model with shelf life and without shelf life. So you can also compare, and then you can do the homeworks and everything without the shelf life. So Felipe, you want to take over, explain
Uh,
a bit the slide, and then go
yeah,
in the
yeah.
app?
Yes. So in order to model shelf life, one of the things that I introduced was a parameter to control the maximum shelf life, essentially the maximum number of time periods during which the products are still usable. And then in order to handle shelf life, I had to modify the example from the previous class, essentially modifying how meet demand is defined, how starting inventory is defined, how ending inventory is defined, essentially splitting them across sub buckets. So now we don't have just meet demand on a certain day. We have meet demand on a certain day from a certain shelf life bucket. Essentially, it can be 0, so it was produced today. It can be 1, it was produced yesterday. It can be 2, it was produced 2 days ago, and so on. And the same applies then to starting inventory and ending inventory, which will then correspond to the amounts available initially for each of the expiration dates, and at the end of the day, how much is going to be there for each of the expiration dates. By doing that split, essentially inventory carryover and material balance then also need to be modified in order to also consider these sub buckets, because now we are just not considering the individual time periods, we are also including the shelf life. And then after implementing this, one thing that I noticed is that the model will not always sell all the inventory first. And these are the things that you can notice in practice. Often you model something, everything seems fine, and then you start thinking, okay, what if the data is slightly different? What will happen? And then one thing that I notice is that sometimes the model was deciding to produce more because there is no penalty on producing more, and there is also no penalty on old inventory. So it could sometimes waste some old inventory and produce instead. So then I'm going to show two ways. One is with an objective, a penalty on the objective, essentially a soft constraint, and another option is with an hard constraint using logic. So let me now share to go into the app. Can you stop shares? Okay. Okay. So here is the app. And like Christina mentioned, I implemented this in a way in which you can see with shelf life and without shelf life. So before just to warm up, I'm just going over essentially the solution of the homework from the previous class. So we have demand and met demand, just for product location periods. Initial inventory, product locations, starting inventory for product location period, ending inventory product location period, and so on. And then we have demand balance. So demand is equal to met demand plus unmet demand. Inventory carryover, essentially starting inventory. If we are in the first time period, is just initial inventory. So the inventory that was already there. Otherwise, we take the ending inventory from the previous time period. So this is how inventory carryover was implemented in the homework. And material balance, it was essentially starting inventory plus the amount that is produced on that time period minus met demand is equal to ending inventory. So it was simple like this, but now let's introduce shelf life. So the parameter that is going to control the maximum shelf life, and then we create this set, an ordered set, from 0 to max shelf life. So 0 is produced today, 1 produced yesterday, 2 produced 2 days ago, and so on, up to max shelf life. And then here are the new variables that I mentioned. So met demand had to be split. So here we have met demand shelf life. That has another dimension for the shelf life. That is for essentially, are we meeting demand from today or from yesterday, or from 2 days ago, and so on. And met demand is this variable here that is equal to the total met demand across all shelf lives. Then the same also applied to starting inventory. So starting inventory shelf life is here, split across each shelf life. The total starting inventory is the sum, ignoring from which shelf life is the inventory. And also the same for ending inventory, here split across the shelf lives. And then there are two things here. So lost inventory is essentially the ending inventory in the last shelf life. So if the inventory is already in the last shelf life today, at the end of the day, it cannot be used tomorrow. So it's essentially lost inventory. And then there is ending inventory, which is the inventory that can still be carried over to tomorrow. So for the sum across all shelf lives, less than the last shelf life, ending inventory shelf life. So now we have these new variables. Demand balance stays the same, so no changes here, but inventory carryover gets tricky, starts getting tricky. So for the first time period, essentially we are going to set the starting inventory to 0 for everything except for the second element of the shelf life, which is essentially yesterday. So here we are saying that the initial inventory being provided goes into the bucket from yesterday. For the remaining time periods, so from for the zeros, essentially for the first shelf life, so here D is the shelf life For the first one, essentially production today, there is no starting inventory, is zero. So is this case. For all the other ones, so 1 day, 2 days, and so on, this is going to be the ending inventory, ending inventory shelf life from the previous day, from the previous shelf life, because essentially we are increasing the shelf life. So if something was there yesterday on the bucket with shelf life 2, today is going to be moved into the bucket with shelf life 3. So every day we move to the following shelf life until there is a point where it is not moved, because the last shelf life does not move anywhere, so is lost inventory. And then material balance. Material balance is now split also across different shelf lives. We have the starting inventory for each of the shelf lives. For the first shelf life, essentially today, we consider production. So the production contributes to that sub bucket. And then from there, we are going to subtract net demand from that shelf life. And this results in the ending inventory from that shelf life. So we are, instead of doing on the daily bucket, we have these sub buckets for each shelf life inside each day. Okay, and this essentially models shelf life. And there are two other things here that I'm going to not mention now. I'm going to just show the solution. Just to show here, for instance, you can see that in this solution, we have zero lost inventory. We have this ending inventory. Everything seems fine. But let's remove two things that I did not mention in the model. So in the model, that constraint that I skipped is the one that forces selling lost inventory, selling old inventory first. And another thing that I'm going to disable, I'm not going to penalize lost inventory. And I'm going to do another thing, because this is tricky to provoke this corner case where we lose inventory without being needed. So let's see, without ending inventory penalty, we can be producing more than we need. And essentially we see here that we are doing production and we are losing inventory because there is no penalty here. So we can produce more and satisfy demand from what we are producing, and not, and essentially, since this is not penalized, lost inventory is not an issue. And in this case, we are allowing also ending inventory to go over, but this can still happen if ending inventory is penalized, because essentially we are not penalizing overproduction. So you can be producing more, satisfying demand from there, and then ending up with a higher value here. And that is not something that you usually want. So one thing that you can say, let's say, imagine that you have a magic way to force all inventory to be sold first. That is one way to do it. You get lost inventory to zero, because essentially now, before you produce or satisfy demand from anything else, you need to first sell all the inventory. Or alternatively, you can use a soft constraint, essentially penalizing lost inventory, so that among all the solutions, the solver is going to look for a solution that also minimizes this lost inventory. So how was this implemented? So essentially, what I have here is how I control this ending inventory for a certain shelf life to be there, if there is, if demand can be satisfied otherwise. So if the way I did this, like in Ample, we can do this because we can write logic and this is automatically reformulated. In other languages, you will need to create BGMs and so on. But here I'm just essentially creating this condition for every ending inventory on a certain product, location, time period, and shelf life. If it is strictly greater than zero, so there is any inventory there, all the demand met must have been with an old, with a more, let's see, with an older shelf life. No. Yeah, so no demand can be met with a newer shelf life. So essentially, if you have a certain ending inventory with like a shelf life 2, you cannot be meeting demand with shelf life 1 or 0. So you need to prevent that. And that's how you do it with this logic constraint. This will automatically turn your problem into a MIP, which is harder to solve, especially at a large scale. Another possibility is the alternative that is penalizing ending inventory. So what I do here is essentially adding this component to the objective, where we have the lost inventory penalty times the lost inventory variable. So these are two ways in which you can control the uh, the lost inventory, and essentially ensuring that you are selling first the the old stock. In the penalty, in case of penalty, you are really not strictly introducing the order. In here, you are really strictly introducing the order. So you really need to sell first the oldest products, then the second oldest products, third, and so on, all the way up to what is produced today. And the other is just doing that with an objective that also handles the same case. So, and this is shelf life part.
Can we go back to the model where you had the penalties? Can you go to the penalties? Sorry.
You want to adjust penalties?
Yeah, can we put the penalty on ending inventory? Because I just
Yes.
want to show, or maybe can you show first the, no, it's running now. Um, like,
You want to see the solution without
yeah, yeah,
penalizing
see
any
the
inventory?
solution
Okay.
without first. Because
Okay.
as you explained very well, you see here you still get some ending inventory because there is no penalty on it, and that's why we need to put it. Because
Yeah.
otherwise, the solver just keeps producing. It meets the demand and say, well, I can produce as much as I want. So that's the purpose of this ending inventory penalty. So now if you go above and put a penalty on ending inventory, it can be whatever, even one or two. So the idea is that this indicates to the solver that I don't want to produce more than I need.
Yeah.
So you see, now it's gone. So that's why you see the power of a penalty, basically.
Yeah. Yes. And the penalties, they are a very flexible ways to handle this type of situations in a way that is not strict and efficient. And the other alternative is really using hard constraints to really ensure that no issue happens. Because one thing also with penalties is that when you start having many different penalties for different things, then at some point you might already be violating what you are trying to prevent with the penalty, because then you have conflicting penalties, and then it can get tricky. And one way to deal with that situation will then be doing hierarchical multi-objective, in which you solve for one objective and then you keep minimizing penalties in secondary, third, and so on objectives, all the way until you have a solution with characteristics that you want.
Right. Yeah, and that's the idea is that you need to, like, because you wonder, how do I know all this? Well, it comes to with the experience, and this is what we are showing you how to do it, and concepts and principles and equations and idea. But then, yeah, it's up to you to go out there and use them, and you learn as you go along, for sure. There is always a lot of learning.
Yeah,
Okay,
because
Felipe, yeah, you want to say something else?
yeah, because this is like the type of tricky things that you only gain with experience. Because often the solutions are going to feel correct, and you will not see, okay, why will I need something to force selling all inventory first, because everything seems right. And with your data it might work. The thing is that later you might see, okay, why is this happening? Why is the model deciding to sell the product produced today when we have stock that we are going to lose? So a bad decision. That is something that you start noticing in real life, and that's also how I started looking for this issue.
Yes, and the idea is that you cannot cover all the possible situations from the beginning when you start writing the solver, because there are so many details and complexities. So then you just need to do it, and then you realize, oh, I forgot to add this. Oh, I forgot to check that. So it's a bit like that. It's not like you're making mistakes, but you cannot capture from the beginning all the details. So you keep building, and then you also keep learning. Okay, thanks, Felipe. Let me go back to the agenda. for next time. So we will continue adding constraints. We are going to talk about transfers. So this intercompany transfers, or how they are called in the ERP context, STRs, STOs. Then we will talk about the target stock, safety stock, max stocks, and we will show you how you can layer them. So for a certain layer, you have this penalty. For a certain layer, you have different penalties. We will also add the purchases, so with the supplier dimension, the storage constraints, and we will talk a little bit about the binding constraints and the restrict table. So this is a way to control what goes inside the solver, like the combination, for example, which product location combinations are good, or lanes and so on. And this is also, let's say, this conversation should also help you with the explainability. Like, how do I explain the results to the user? How can I control the results such that they make sense to the user, and so on. So thank you for watching. If you have questions or suggestions, let us know, and we will see you next time. Thank you. Bye.